Notice a single phase. Notice the polarity of these, plus to minus, plus to minus. So what's a single phase 3-wire system or source? If I was to write the definition of that, I will say a single phase three-wire source is a source having three output terminals. Notice A, N, and B. And the phase voltage, if I call this VAN, is equal, this is NB, notice the plus on the top, the minus on the bottom. And VAN will equal VNB. There is no phase shift. So if this value, for example, is 115 angle 0, this will be 115 angle 0. Same thing. And if you measure the voltage from A to B, if you go and measure that voltage from A to B, it's going to be VAN plus VNB, which is twice, since these guys are equal, twice VAN. So in this case will be what? 230 angle 0. Where do we use that? We use that in the US. In North America, we use that all the time. When you want to get 220 volts at home, that's what we use actually. If you have electric stove at home, if you have electric dryer that requires 220 volts, we take 110 and 110, connect them like this, a three-phase, single-phase, a three-wire system, and get actually the 220 volts that you need to run your stove, your washing machine, your dryer. Washing machine actually normal plug, but the dryer, electric, some of the dryers actually still use normal 110, but the bigger ones need 220. Your stove is usually 220 volts. And that's how we get that. Let's take an example on that. One problem that requires or uses single phase 3-wire system, and we'll use 115 angle 0. And let's put a 1 ohm here, resistor. Let's put a 1 ohm. This is basically the resistor of the inside the wire, or the wire itself. It's not a perfect wire. And now we have a load here, 50 ohm. We have 100 ohm here. And we have one at the end of 20 plus J10. Load 1, load 2, load 3. So this is load 1. This is load 2. And this is load 3. L3, load 3. L1, L2. These are the transmission resistance, the wire itself there. So let's calculate the power delivered to each of the three loads. Find the power delivered to each of the three loads. And maybe we'll also, while we add it, let's find the power lost in the lines. This is, by the way, this is the neutral. That's capital N. We always notice I use lowercase for the source, uppercase for the load. That's common. And this is B here, and this is capital B. The wire lost in the wires. We're talking about the three resistors, the three 1 ohm resistors. How much power lost in them? If I know the current through each one, I can tell you all the stuff. So maybe I should shift my focus on finding the current. Well, how do we find the current? Let's assign some currents in each one of them and write three equations by three unknowns and see if we can find what these currents are. Use KVL. So right now I'm not answering any of these. I'm going to find the current going through each one of them. I'll take a nice sheet of paper, put on top of this, leave this picture up there, and let's do KVL for loop 1. Right there. Sum of the voltage in a closed loop is 0. So if I travel this way, I'm entering the source minus to plus. Me, I use negative for that. I said that probably 10 times. I'm the opposite to all these books. They use positive for this, negative for that. Mathematically doesn't make a difference. This will be a plus. When I travel through that, notice I'm marking this one plus, minus, plus, minus, plus, minus. I'm traveling this way. So that'll be a plus 1 times I sub 1 plus 50. Since I'm going plus to minus, I need the current down. What's the current down through that one? Through the 50 ohm. Yes, I sub 1 minus I sub 2. Plus, I'm traveling this way, so what's the current to the left here, from right to left through the 1 ohm? I sub 1 minus I sub 3. And if I clean that, I will have 115 angle 0 equals. Let's see what we have for I sub 1. 1 plus 50 plus 1. Is that 52? Minus 50 I sub 2 minus I sub 3 equals to 0. So there's equation number 1. I took this problem from the book, actually. If I wanted to match that, they had a 3 here, not a 1. That was a 3 there, I just noticed that. So let's put a 3 there so I don't have to, I can cheat and use their numbers. So this is a 3. So if that's a 3, this will make it a 3 here, right? And instead of 52, this becomes what? 54. Trying to speed up the process so I can steal the answers from them. I don't have to do the math. And this will be what, 3? Yep. I thought they're all 1s, but I was wrong with that one. Now let's do KVL for loop number 2. Is there room on this? Is there still room on the bottom? I could, yep. So KVL for number 2. And this is number 2. Let me start with this one. Again, I'm traveling clockwise. So I'm looking at it plus to minus for this one. Through this loop, I'm looking at it plus to minus and plus to minus. I'm going clockwise. So the first one, 20 plus 10J. And what's the current through that? Is it I sub 2? I'm starting with this one. Let's continue. I want plus to minus. So here we go. Plus 100. Since I labeled this plus to minus, I'm looking for the current up or down? Up. And what's the current up? Yes, I sub 2 minus I sub 3. Plus the 50 here. And again, I label this plus to minus, so I'm looking for the current up, which is what? I sub 2 minus I sub 1. And if I clean that one, what do we have? Negative 50 I sub 1. Let's see I sub 2. We got a 50, 150, 170, plus 10J I sub 2, minus 100 I sub 3 is equal to 0. And that's equation number 2. That's equation number 2. Everyone's all set with this equation? Let's do loop number 3, KVL, loop number 3. Again, I'm traveling clockwise inside this. I'm looking plus to minus, plus to minus. So I'll begin with the source. That's a negative 115 angle 0. Plus, that's a 3. And notice I label plus to minus. I need the current going to the right. What is the current to the right? Is it I sub 3 minus I sub 1? Plus the 100, and I label this inside the loop plus to minus, so I need the current down, which is what? I sub 3 minus I sub 2. Clean it. 115 angle 0 equals negative 3 I sub 1, negative 100 I sub 2. And what do we have? Plus 3 I sub 3? Oh no, 103, right? 103 I sub 3. And that's equation number 3. So now I have 3 equations by 3 unknowns. Did I leave it out? Oh, it looks like I left this guy out. Yes, I might have had it covered. Good eyes. I left the resistor on the bottom. That'll make it what, 104 now? Thank you. So now I got 3 equations by 3 unknowns. And if I plug them into the calculator, here's what I sub 1 is equal to. 11.24 angle negative 19.8. I sub 2 equals 9.4 or 9.39 angle negative 24.5. And I sub 3 is equal to what? 10.37 angle negative 21.8. We're looking for the average power absorbed by each one of these loads. Each one of these loads. So let's look at the average power absorbed by the 50 ohm resistor. I need to know the current down through that resistor. Remember, average power absorbed by a resistor, we can find it by what? Using, what is it? I times V. Well, there is no cosine. It's going to be a 0-degree phase shift here, right? These are RMS values, by the way. I forgot to mention. So I'll do that. I'll write it down. RMS, VRMS, cosine, I'll put that there. Theta V minus theta I. Well, through a resistor, there is no phase shift. This will be a 0. So it's IRMS times VRMS times cosine 0, which is a 1. And if I use Ohm's law, V equals I times R, this will be I squared. Or if I have the voltage, I can use V squared. I can use any one of them. Well, I know the current through this resistor. I know the current down. The current down is I sub 1 minus I sub 2. So what is the power through the 50 ohm resistor? It's the magnitude, not the current. It's the magnitude. Because if you find the current, you know what? Let me find the current through it so you don't get confused. What's the I through the 50 ohm resistor? I, the current. Through the 50 ohm resistor, the current is going to be what? I sub 1 minus what? I sub 2. And my calculator, let me get it again and plug these numbers in. Where'd you go? Come on, clear everything. Clear, clear, exit, quit. Okay. Where was I sub 1? Here we go. 11.24 11.24 angle negative 19.8 minus, and what was I sub 2? 9.39 angle negative 24.5. You take the difference between them. And the calculator says it's 2.03 angle 2.44. So what is the average power absorbed by the 50 ohm resistors? The magnitude of that, which is 2.033 squared divided by R. And what is R here? R is 50, right? Oh yeah, the I squared times R, thank you. V squared over R. I should go back to bed today. So 2.033 squared times the 50, which is what? Roughly 207. 206.6 watts. Let's look at load 2 here, this one. I need to find the current through load 2. So what is the current I through that 100 ohm resistor? So it's I sub 3 minus I sub 2, and again, let me jump on my calculator here. Clear this one. I sub 3, which is 10.37 angle negative 21.8 minus I sub 2, 9.39 angle negative 24.5. And I came up with 1.085 angle 2.27. So what is the average power absorbed by the 100 ohm resistor? Is going to equal I squared RMS times R, which is 1.085 squared times the 50. 1.085 squared times the 50, 100, not a 50. Right, the resistor is 100. The previous one was a 50. Boy. Is it 117.7? So I'll go 118 watts. And what is the average power absorbed by the 20 plus J10? Well, if you remember, the inductor will have an average power absorbed of what? 0. Average power absorbed by inductor or capacitor is always a 0. Why? Cosine theta V minus theta I. The difference between theta V and theta I is going to be either plus 90 degrees or minus 90 degrees. And what's cosine plus 90 or cosine minus 90? 0. So the average power absorbed by that inductor is 0. I only have to deal with that resistor. So that's why the average power absorbed by the 20 ohm resistor only, which is I squared R. I for that happens to be I sub 2, which is 9.39 squared times R, which is 20. $1,763 watts. Okay, now let's look at the lines here. So let's find the average power absorbed by these three wires. We'll start with the 3 ohm, the neutral one. Well, we need to the current through that. Well, the current through that, I sub 1 minus I sub 3. We take the magnitude of that and we square it, then we multiply it by the resistor, which is 3. Well, the value of that current, when you subtract them, I was doing that, 0.948. Square that times 3. It is 2.69, how about 2.7? We'll go 3 watts. The average power absorbed by the 1 ohm resistor. We know what the current through that. That's I sub 1 RMS squared times R. And I sub 1 for that is 11.24 squared times 1. And that's 126 watts. And what's the power loss by the bottom 1 ohm there? It's I sub 3 RMS squared times R. And I sub 3 for that one was what? 10.37 square it times the 1. And that's 108 roughly.
That's P2 right on the bottom?
Well, this is the 1 ohm resistor I was labeling.
Okay.
Yeah, by the resistor. Bless you. How's that? The 1 ohm resistor on the bottom, that's the 1 ohm resistor on the top. So I write top here, bottom. You know what, while we at it, let's see how much power was absorbed, taken by all these values. So the total power absorbed is equal to it. Well, I see the 108 from here. I see the 126. I see the 3. From the previous example, we have what? The 207 for the 50 ohm resistor. We have what? 118 for this one, the 100 ohm. And we have this load 1,763. So let's see. That's the total. 108. I wasn't planning on doing this. If I did, I would carry more decimal places. But you know, I changed my mind. I said, oh, let's add that to it. And I came up with the value of 2,325 watts. Now let's see what the average power is supplied by the source. And maybe I can find the power factor. That would be cool, actually. I wasn't planning on doing that, but let's do it. What is the power supplied by the source? The average power. Let's look at the average power supplied by the source AN. Again, the average power, VRMS, IRMS, cosine theta V minus theta I. For the top one, the VRMS is 115. And what's the current? Isn't that I sub 1 going through it? I sub 1, I forgot what I sub 1, 11.24. Cosine, what is theta V here? 0 minus, what's theta I for I sub 1? What was the negative 19.8, right? So that'll be a plus 19.8. And this is supplied here. So this is supplied, both of these, the sources. So 115, not 0.5, 115 times 11.24 times the cosine of 19.8. 1216 roughly. And what is the average power supplied by the other source, NB? This source. That's also supplying power. Why? Because the current entering the negative end. It's 115 times the current I sub 3, in case you forgot what I sub 3, because I forgot, 10.37 angle 21.8, negative here. 10.37 times cosine 0 minus, and what was it, 21.8, that becomes a plus 21.8 degrees. $115 times 10.37 times cosine of 21.8. 1107. What is the total power supplied? Which is 1107 plus 1216. 1216 plus 1107, and that is 2,323. What was the average power supplied? 2325. Absorb 2325. The difference, why? Rounding error. Now let's look actually at the load itself. What did the load get? What is the total power delivered to the load? Just these three, not these resistors, but these three. The total power delivered to the load is what? Let's look at the 50, the 100, and this one, and how much power was absorbed, average power by each one. Just the three of them. It's 207 plus 118 plus 1763. $207 plus 118 plus 1763. 2088 watts. So how efficient your system is. Basically, what's your power factor? What are you getting? This is the load. These are lost in the wires going to the load. This is your factory. This is your house. These are the wires coming to your house, and you lost that much power in them. So what is the efficiency or power factor? Well, how much did you get? You got what? 2088. Out of how much? What is the power supply to the house, the whole load there? How much the total power? Total power supplied, 2323, my rounding. And what are we getting there? 2088 divided by 2323. I'm getting about 0.899. So I'm actually getting 89.9% of the power. If this is my load, my house, my factory, I'm getting 89.9% of the power being supplied to my house. I'm losing 10% through these wires. We end up with a better problem than I thought we were going to have. Initially, the plan was just calculate the average power absorbed by the load, the three loads, and the average power absorbed by this. And we opted to go through it. Now let's look at a three-phase Y-connected source and load. Time looking at, okay, we have time. Stop the video.